What's up, guys? Welcome to another video brought to you by The Simple Engineer. Today we're going to be discussing a very popular algorithm known as Quicksort. And in this video I want to talk about kind of the high-level intuition, visual depiction of what the algorithm is solving, what it's attempting to do. I want to basically go over the implementation. We're going to be doing that in Java. And then we're going to be spending a fair amount of time in this section where we will be analyzing the time complexity for average, best, and worst case for this problem. And then finally we will end it with a fun little whiteboarding problem known as the Dutch flag problem, which is kind of tied together with Quicksort. So without further ado, let's go ahead and get started. I want to talk about kind of what exactly is Quicksort doing. So when you're given an array of integers or whatever comparable values that you're trying to sort against, what is Quicksort aiming to solve? So let's say that we're given just an array of integers 1, 0, 10, 15, 26, 12, 5, 3, and 7. So this is a pretty scattered array. At the end of the day, we want to get this in increasing order, so from lowest to highest number. And Quicksort says that it can do that. It says it can do it relatively quickly as well, and we'll talk about that more, but the quickness of this algorithm is in log n, and we'll go ahead and derive this kind of later on in the video. But what we do is we essentially go through a relatively simple comparison process. First thing we do is we pick a pivot, so we can pick the last number in the array, and we start at the beginning, and we basically have two iterators. What are the iterators? Well, we say we can initialize some I to -1, and we initialize some C to 0. Now, breaking down the names here, the C value is going to be tracking our current iteration within the array. So we're going to iterate from the 0th index all the way to basically the pivot -1 index to do these comparisons. And the I is only ever going to increment every time that we do a swap. Now, what's the purpose of that? Why do we have two iterators? Well, what this guy is essentially doing is he's storing the location for the pivot, when the algorithm completes. So obviously the goal here, what we're doing is we're solving subproblems. So this kind of falls in the category of divide and conquer. We don't solve or sort everything in the first initial pass. We solve all these subproblems. And the subproblem states that we want to get a pivot, and we want to ensure that everything to the left of the pivot is less than the pivot value, and everything to the right of the pivot is greater than the pivot value, all being compared against, in this initial pass, the number 7. So at the end of the day, once we hit this last index value, we need to say, okay, now let's put 7 in its correct spot, because we still need to satisfy this criteria. Well, where are we going to put it? We're going to put it to the right of I. And that'll make more sense as we continue on. But that's the reason that we have two index trackers. So what happens is we go through, we're basically in a for loop is how you can visualize this, and we're saying, okay, is 1 less than 7? Yes, it is. So in the case that the value, we'll call this A, in the case that A of C is less than or equal to the pivot value, then we want to perform an increment on I, so I++, because this is saying that, oh, the pivot could potentially be swapped here, so we want to ensure that this is up to date. And then we want to swap C and I. So we want to swap A sub I and A sub C. Well, in this initial pass, it may seem a little bit goofy because I gets incremented to 0 and C is 0, so we're swapping with ourselves. And that's totally fine. That makes sense. And we're just going to continue on through, and we may have to do something odd like that a couple times. And then, of course, within the for loop, we're just going to increment C every single time. So I is now 0, C, well, C is now 1. Okay, is 0 less than 7? Yes, it is. So what are we going to do? Well, we're going to do this logic. This is kind of our comparison logic. We're going to increment I, so I is now 1, and we're going to swap 1 and 1. Okay, so again, we're swapping with ourselves, so we do the swap. It yields really no change at all, and then we increment C. So C equals 2. Well, is 10 less than 7? No, it's not. So we don't do anything other than increment C. So C is 3. 15 is not less than 7, so we continue. C is 4. 26 is not less than 7. C is 5. 12 is not less than 7. C equals 6. Okay, well now we have something interesting. 5 is less than 7. So what are we going to do? Well, we're going to increment I from 1 to 2, and we're going to swap C and I. So what happens in this case? Well, what happens is I is at 2, because this is zeroed index. So 0, 1, 2, and 3, 4, 5, 6, 7, 8. We're going to swap this value with 2. So 5 now comes over here. So this becomes 5, and this becomes 10. And then we carry on and we say C equals 7. Okay, well 3 is less than 7, so we do the same thing. I is now 3, and we swap I and C. Well, C is 7, I was 3, so now this turns into 3, and this turns into 15. Well, now our current value has hit the pivot, and we only do this up until we hit the pivot. So now what do we want to do? Well, now we want to ensure that this criteria is still satisfied. So 7 needs to get moved into its proper position. Well, keep in mind, I ended at I equals 3, which is here. Now, for this criteria to be satisfied, we essentially just need to move 7 into the I plus 1th position, which will be right here. So at the very end, what we're going to do is we're going to swap in the A array. Essentially, we're going to be passing in the index for the pivot, so the pivot index, and we're going to be swapping this with I plus 1. And then we would return that pivot index that we had just swapped with. So now this is going to go right here, and then 26 would get moved to where the 7 is. So what would this look like? It's getting a little bit messy, but we can just show what the final array looks like. So we have a 1, 0, 5, 3, and then of course we have the 7, which was our pivot, 26, 12, 10, and 15. So what do you see here? You already kind of see that we're starting to sort the algorithm, because everything here is less than 7 and everything here is greater than 7. And this is where divide and conquer comes into play. So I'm not going to go through all the steps here for the visualization, but what you'll notice and what we'll implement is that we're going to be recursively applying this solution to the left subarray and the right subarray. So now that we return this pivot index, we can say, okay, let's only do this logic that we just did up here on this little guy here. And let's do it again recursively on this little guy here. All using this as a reference point to know where exactly we can start and end within Quicksort. And then what's going to happen? Oh, well, the solution space is going to shrink, and it's going to shrink. And then we're going to get one value. And then as this continues to go on, we get one value. Oh, well, when you sort only a single element, it is itself. So this is going to turn into 0, 1, 3, 5, 7. And then once the recursion ends here, it's going to turn into 10, 12, 15, and 26. And that's our goal. And that's what we want to code. So really, the overall idea is we loop through, and under this case, if the current value is less than or equal to whatever value is stored in that pivot index, increment I, so track where pivot is going to shift at the very end, and then perform a swap with C and I. And this ensures that the lesser values are to the left of the pivot, and the greater values are to the right of the pivot. So let's go ahead and code this. Hopefully that explanation was clear, and if it wasn't, hopefully it becomes more clear in the implementation. So we're going to create a class, public class, Quicksort, and we're just going to go ahead and say public static void main, and I'll rename this here. Okay. So we'll have a driver here just to test, but before we even worry about that, we're going to go ahead and code our first algorithm. So the first piece of the algorithm is going to be this sort, and it's going to be done in place, so it's not going to return anything, and this will just be called sort. It's going to take in the data array that we care about. We can just call it data array with the lowest index that we start with, and of course the highest index, which is the length of the array. Like I said previously, this is going to be a recursive algorithm, so we need a base case. And the base case for breaking out of this recursion is if the lowest index is greater than the high index, then you break out of it. Otherwise, we'll just continue. So as long as the lowest index is less than high, then we're totally good to continue recursing and applying this kind of partitioning and sorting, divide and conquer approach. So first thing we want to do is get the partition value. This is going to say, okay, if we do the initial pass, basically what we described here, we want to figure out what index is this going to end up at as we go through all these subproblems each time. So what we're going to do for that is we're going to say partition is simply equal to a function that we'll write, which is going to take in an integer array, the low index and the high index. Then from there, we use this value to then determine how do we sort all of the rest of the subproblems. Well, like I said, if we have this value, then we know that we can quicksort from 0 to pivot -1, and from here we can quicksort from pivot +1 to the end. So that's exactly what we're going to do here. We're going to say, all right, let's go ahead and sort the data array. We're going to do it from low, which is the lowest value, to partition -1. And then we're going to sort data array from partition +1 to high, and that should be all we need for this function. So this is basically going to recursively sort the subproblems within our integer array. Okay, so then we're going to code another function, make a static function that will return an integer, and this will be our partitioning function that will have a similar method signature to the sorting function. And what it's going to take is going to take an integer array, call it data array. It'll take in a low index again, and it'll also take in a high index. So what is this doing exactly? Well, this is basically determining the index of the partition for the particular subproblem that we are solving. So, similar to the algorithm, we said that we had two iterators. First one was that kind of random I iterator that tracks where the pivot should be shifted at the end of the algorithm execution, and that was just low -1. And then of course we had the pivot value, which was int pivot is simply equal to data array of high. So this is going to be just the default to the last element in the integer array. Okay, so now from here what we want to do is we just want to iterate through all of the elements. So looking back at the picture, we kind of go in one by one, and we say c equals 0, c equals 1, c equals 2, all while performing the constant comparisons in the process. So we'll say the current value is equal to whatever low is, and then we need to ensure that current is strictly less than high, non-inclusive, and we will increment current through each iteration. And this is where we do that simple comparison check. We're just going to say, okay, if the value in the data array, so data array sub current, is less than or equal to whatever our pivot value is, then we want to increment I, so increment the tracker for where the pivot will be shifted at the end, and then we want to swap current and I. So this swap current and I to ensure that lesser values remain to the left ensures greater values remain to the right. So what I want to do is just code a simple swap algorithm. So we'll just, or a swap function that'll say public static void swap. It'll take in an integer array. It'll take in an index 1 and an index 2, and essentially we'll just say temp equals a sub index 1, a sub index 1 equals a sub index 2, and then finally the last swap will be a sub index 2 equals temp. That'll be done in place, so we can simply just call swap data array with current and I. Okay, so it'll continue incrementing and swapping up until we hit the pivot itself, which is this guy. So this is the index of the pivot. So what do we want to do? Well, we want to swap now. We want to put the pivot in the proper position. So in order to do that, we want to swap in the data array with I plus 1 and whatever the high is. And high in this case is referring to the index of the pivot, whereas pivot is referring to the actual value in the array. And then from there, once we do the swap, we can simply return I plus 1. And I plus 1 will be the corresponding index of the pivot that we're dealing with. And that should technically be it. So let's go ahead and create a main method to go ahead and test this, and then we can do a recap. So create an integer array. We'll just call it data, and we'll fill it with, well, I guess we can fill it with the same values that we had here. So we had 1, 0, 10, 15, 26, 12, 5, 3, and 7. And now what we want to do is just simply say, well, we can call sort on data, and it will start with the 0 index and data dot length minus 1. And then we will look at the values. So if we just put a debugger here, we can go ahead and debug this. Okay, so we're going to execute sort. Okay, it just finished. So if we look at the data, you see that we have 0, 1, 3, 5, 7, 10, 12, 15, 26. So all of the data after the execution of the sort function was indeed sorted correctly. So let's go ahead and do a quick recap. So a quick recap is we call sort, which is essentially kind of our driver for kicking off the Quicksort algorithm, or the bulk of the algorithm, I should say. First thing we want to do is find that partition, or what is the value in which all values to the left are lesser than the pivot and all values to the right are greater than the pivot. And then we want to essentially apply that logic recursively until our base case is satisfied. So looking at the core of the algorithm, we're basically just iterating through, and any time that the current value is less than or equal to the pivot, then we simply perform a swap. And this allows us to ensure that criteria of lesser values to the left, greater values to the right. And then of course we return I plus 1, because as we're tracking where the pivot value should be moved at the end, this is that last element. So right after that is where the pivot will go. So now we can continue on through, and let's go ahead and talk about the complexities. So the complexity analysis of Quicksort can get pretty mathematical. So we're going to look at it from 3 different perspectives. We're going to look at Quicksort from its best, average, and worst case. And we'll actually look at average last. So first let's look at best. We know, we've heard through the grapevine that Quicksort has this time complexity of big O in log n. And that's really fast. That's really good, and that's why a lot of people like it. But how do we actually get that? What I want to do is I want to derive the recurrence relation for doing so. And what better way to do that than actually pulling up the code and analyzing it one by one. So I'm going to go ahead and screenshot this. And we'll just go ahead and load it up into the program. So let's see here. All right, so this is our code. Now what I want to do is I want to look at each piece and figure out what is the associated time complexity of each piece. Okay, so if we're looking at down here, we have low less than high. Okay, well something like this is simply constant operation. Partition, we haven't looked at that yet, so we don't know. But, and keep in mind this is best case, when we're looking at the sort function, we're essentially saying, okay, from low to partition minus 1 is the left subarray. From partition plus 1 to the right is the right subarray. So we're essentially looking at half of the input space for each of these recursive calls. So here I could argue that this is t of n over 2, and over here I could argue that this is also t of n over 2. Okay, so now let's look at partition. Partition, we have a bunch of constant calls again. So this is O of 1, this is O of 1. For here we have a for loop, and within the for loop we have essentially a few constant operations as well. So for each iteration we have a set of constant operations, so I could argue that this would be something like alpha n. And then of course at the end we do a couple swaps here. For all the swaps we can assume that we just have constant operations. So at the end of the day what I'm seeing is I'm seeing that we essentially have a recurrence relation that would be equivalent to say t of n is equal to, we have 2 of these guys, 2x, so we could say t of n equals 2t of n over 2, and then we're adding basically alpha n number of constant operations for the actual partitioning, and this is what we need to solve. So if we go ahead and we create a new kind of workboard here, we essentially need to solve t of n is equal to 2t n over 2 plus alpha n. Okay, well this actually isn't too bad. What we can do is we can start with substitution. So just a simple substitution recurrence relation, we can say, okay, we're looking at this, but what actually is t of n over 2? Well, let's go ahead and solve it. We can say t of n over 2 would be equivalent to 2 multiplied by 2t of n over 4 plus alpha of n over 2, and then we would be adding alpha n. So what I like to do when I solve these is I like to continue to simplify to kind of reduce the amount of math that we develop. So we'll say this is equivalent to 4t of n over 4. So 4t of n over 4 plus 2 alpha n over 2 plus alpha n, and this reduces to 4t of n over 4 plus 2 alpha n. And now we kind of continue through. And what we're ideally trying to do is we're trying to figure out where's the pattern, or what's the pattern. For me, I can't see the pattern yet. So I know that this is kind of the base case, the initial iteration. This is number 2. Let's go on to number 3, and hopefully we see a pattern around number 3 or 4. That's usually how long it takes. So here, this is kind of our finalized case here. This is our finalized case here. And now we can say, okay, well, now I want to see what t of n over 4 is. So I'm going to say, okay, t of n over 4 is going to now be equivalent to 2 multiplied by, and essentially what you can do is you can just take, okay, t of n is this, right? So what I like to do is simply just substitute n over 4, so we can have 4 multiplied by, and this would be n over 4, so we can say 2t of n over 8 plus alpha of n over 4. And now what we can do is we can add 2 alpha n, and this would simply reduce to 8t n over 8 plus 4 alpha n over 4 plus 2 alpha n. We get a final reduction to be 8t of n over 8 plus 3 alpha n. And we may have actually already found ourselves a pattern, because here we have 2, 4, 8, we have 2, 4, 8, and we have kind of a coefficient of 1 here, coefficient of 2, coefficient of 3. I would argue that we have already found a pattern. So what we can say is, well, this is essentially, for each iteration, we're multiplying by an exponent of 2. So we can say this is 2 to the k, and the recursion call turns into n over 2 to the k. And then what are we adding? Well, what we're essentially adding is we are adding whatever the kth iteration is multiplied by alpha n. And this is what we need to solve. Well, we need to keep in mind, what is the base case of what we're trying to solve? The base case. The base case for our recursion loop is t of 1 equals 1. When we have one element in our sorted array, we're just going to return ourselves, because when you try and sort yourself, you are already sorted. So this is our base. So now we essentially just need to solve simple logarithmic problem. We know that the base case is t of 1, so if we equate this kind of mid piece here, n over 2 to the k to 1, and solve, we're closer to being able to analyze the time complexity. So we can essentially say n over 2 to the k equals 1. We can cross multiply, and from here we can just take the log of each side. So log 2 of n equals log 2 of 2 to the k. And through reduction, we can equate k to be equal to log 2 of n. So this is a very important piece here, because now what we can do is we can look at our original formula and we can say, okay, well, if we have a k here, then what do we have? Well, we have 2 to the log 2 of n, it's just substituting k here, multiplied by, and for this to hold true, we set this to 1, so this is just multiplied by 1, and then we multiplied k, which is just log n, so log base 2 of n multiplied by n multiplied by alpha, which is just some constant. So if we reduce this guy, what we have at the end of the day is we have 2 raised to the power of log 2 of n, which is just simply this gets reduced down to n using logarithmic properties. So we have n multiplied by 1, and then we simply add n log n, and then our number of constants, which we can pretty much ignore. So the highest value in our recurrence relation is n log n, which is how we get a time complexity of n log n for our best case. Now I want to continue on and analyze what exactly does it mean to have a worst case. Worst case can yield an n squared explosion, which can really ruin the benefits of our algorithm if we are not careful. So let's go ahead and discuss that. So looking forward here, grab a color. Alright, so how do we get a worst case? Well, in worst case we have an input array that is already sorted. So we have 1, 2, 3, 4, 5, 6, 7. So if we have an already sorted array, we need to think back, what exactly does our algorithm look like? Well, we had that sort function, right? And this sort function was kind of recursively calling itself. So, you know, it had its method signature with the array and the indices, and we called the partition function. And this kind of yielded the index that we needed to partition against, and we had already determined that the time complexity of this was something like alpha n plus constant number of operations. In addition to this, we called sort, which was itself. And it was kind of from, you know, 0 to p minus 1, and then we called again for, you know, p plus 1 to, you know, whatever the length was, basically. And this was recursively applied, but this was kind of the overall idea. And with the n log n benefit, we were noticing that we were getting n over 2. T of n over 2 and T of n over 2. We were essentially having our search space. And that was really good. And that's best case scenario. But in this case, when we have an already sorted array, what we're doing is the partition is not really doing us much benefit because the left subarray is all elements to the left of our pivot. So the input space for when we call sort ends up being somewhere along the lines of T of n minus 1. We haven't really reduced our search space at all aside from this minus 1 for our pivot, and there is no right subarray. So this was kind of representing our left subarray that we wanted to solve, and this was representing our right subarray. But since this doesn't really exist, this is more like a constant operation now. So at the end of the day, what we have to end up solving is a recurrence relation that looks like T of n equal to T of n minus 1 plus alpha n plus Cn. And this reduction will allow us to see kind of the negative benefits of feeding in an already sorted array into something like Quicksort and how it yields that n squared explosion. So let's go ahead and demystify the solution here. So we're going to do a simple substitution on this recurrence, and we're going to say, you know, we want to solve for T of n minus 1 and find the pattern. So T of n minus 1 is going to be equivalent to T of n minus 2, and then we'll just add, you know, some alpha for n minus 1 plus alpha n. This will actually further reduce, so this will reduce down to T of n minus 2 plus 2 alpha n minus alpha. So this from the first iteration, or I guess we'll call this the iteration 1, we'll call this iteration 2. Now we'll continue on to iteration 3. We're going to now solve for T of n minus 2. So T of n minus 2 will be equal to T of n minus 3 plus alpha of n minus 2 plus 2 alpha n minus alpha. So this is kind of a big one, but we'll go ahead and easily reduce this to t of n minus 3 plus 3 alpha n minus 3 alpha. So I wager that we can now argue that we see a pattern. So say this was our initial guy, this was iteration 2, iteration 3. What do we see here? Well, we see that the coefficient here is incrementing by 1. We see that this value subtracted from n is incrementing by 1 as well. And then we see that the coefficient for this guy over here is kind of actually, so we have an alpha here, we have a 3 here. Maybe we want to go one more step because we're actually ignoring constants here, but what I see is this goes from alpha to 3 alpha, so there could be even a more interesting pattern. So let's go ahead and solve t of n minus 3. T of n minus 3, also another simple reduction. This would be t of n minus 4 plus, I guess this would be alpha of n minus 3 plus alpha n minus 2 alpha plus 2 alpha n minus alpha. So simple algebra at the end of the day, this will just yield to n minus 4 plus 4 alpha n minus 6 alpha. Okay, so now I think we can see a more interesting pattern. These numbers 1, 2, 3, 4, they're still staying the same. The coefficients are incrementing by 1. But now what I see here is this is 1, 3, and 6. So let's go ahead and try and demystify this pattern here. So go ahead and create a new color. What I'm actually seeing is I'm seeing that we have something like n minus I, and then we are adding the same I. We're multiplying by alpha, and we are multiplying by n. So I'm just looking at kind of this skeleton structure here and substituting the genericized version down here. And then what I also notice is that we are subtracting kind of we got a minus 1, a minus 3, a minus 6, and what that looks like here is we have a minus 1 plus 2 plus 3 plus dot 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 k minus 1 into alpha. This right here is a simple arithmetic progression, and arithmetic progressions could simplify a problem like this to n minus I plus I alpha n minus, and we would just have something like k minus 1 divided by 2 multiplied by alpha. So now we need to kind of solve the base case. So we already know that the base case is t of 1 equals 1. So this was t of n minus I plus I alpha n minus this value. So we need to simplify this. T of n minus I, this equals to 1. We can say n minus I equals 1. N is equal to 1 plus I. We can disregard all negligible constants, and we're essentially saying that n and I are the same. So what does that leave us with? That leaves us with this final element here. This turns into 1 because of our base case. This is our base case. This over here essentially turns into n squared because I and n are the same, so this becomes n squared by alpha. And then we're subtracting k minus 1 divided by 2 multiplied by alpha. So if we look at the largest term, this is a simple quadratic expression, but the largest term is n squared alpha. And when we are analyzing time complexity, we're of course going to look at the largest value and deem that in this scenario, which is unfortunate, we get an n squared analysis. So let's go ahead and figure out how can we prevent n squared in Quicksort, and how can we get an average case of n log n? Is it possible? Yes, it is. So close this guy. We'll talk about average case. So we also wager that the average case will yield n log n if the implementation is done correctly. So what exactly do we need to do for the average case? Well, the average case gets interesting when we pick our pivot. Before, when we were determining our pivot in the partition, we kind of defaulted and just said, you know, pivot equals whatever our array sub high. And that was always defaulting to the last element. But what if we did something a little bit more interesting and we randomized the pivot? So instead of always defaulting to this concrete value, we could randomize this. That way, probabilistically, we would have better odds of reducing our complexity because we would be picking a pivot value from a uniform random distribution. So essentially, what we would be doing is when we call our partition, essentially, we would have a function here called random partition. And now what we would want to do is we would want to say, okay, in random partition, let's just go ahead and immediately swap. We're just going to swap in our data array some random index. So this random index will be swapped with the very last index. So that way we can still have, the pivot will still be at the end. It's just that we have now picked from an equal probability a value randomly from the array that we will now place at the end instead of always defaulting to the last value in the array. And this will be a random partition. So we can call this, and then from here we'll just kick off our partition algorithm like we did before. But this will give us kind of that equal distribution. So now if we look back at our partition or our sorting algorithm, we had something like sort that took in the array, the low, and the high, and we were calling partition to get our partition index. So partition index, and we had deemed again this was alpha n plus cn. And then of course we did our left subarray, so we sorted from, you know, a low to p minus 1, and we sorted from a p plus 1 to high. Okay, now from here though, what are we actually doing here? The pivot lies at an index I, right? So if a pivot lies at an index I, then we're dealing with a search space of t of I minus 1 because we're dealing with all elements to the left of that ith index. Now, the array index is between 0 and the end of the array with equal probability because of our random partition. So we have t of I minus 1. Now for the right subarray, we have something like t of n minus I. Now, this is kind of similar to the end, right? We're dealing with everything to the left of the pivot. So this is essentially representing the pivot that was chosen with equal probability instead of just always defaulting to the end. And then this is everything less than that, and this is everything kind of greater than that pivot. So what we're trying to solve at the end from a recurrence perspective is we're trying to average out the values. So we would have something like t of n is going to be equivalent to 1 over n multiplied by the summation of I equals 0 to n minus 1. And then we would have our recurrence values that we care about. So we would have t of I minus 1 plus t of n minus I. And then we'll just go ahead and add plus some constant number of operations for the rest. And we're not going to solve this in this video due to time, but what I will tell you is the reduction of this average formula here will reduce to in log in average time case. So this is definitely preferred here.